Hey Alex, how's it going, man? Wanted to go through your test review here and just kind of go through them in order. So I'm going to go through and just work through the answers. I would definitely recommend giving each of these a shot yourself, see what you're able to answer, and then come listen to my answer afterwards. So if you do it all yourself and then you get the same answer as me, then you know that you are good, and then you can yeah, you just be confident in that. But otherwise, then you can see specifically what gave you a hard time. So definitely give it a shot before watching this. But let's just go through these in order. So question number 5 reads, the dot plot shows a random sample of the number of migrating geese flocks observed by 25 participants during a 2-day hike. And so I will admit, this graph was really difficult for me to read at first. I thought it was saying that 4 times there was 4 flocks of geese observed, but that's not what it's saying. Each one of these dots represents one of the 25 participants' answers. So if I asked one person, hey, how many flocks of geese did you say? One person said, I saw 6 flocks of geese. The second person said, I saw 5. The third person said, I saw 5. The fourth person said, I saw 7, all the way until, like, this is plotting their answers. So what we end up having here is 4 people answered, I saw 4 flocks of geese. There were 7 people that answered, I saw 5 flocks of geese. 7 people answered, I saw 6 flocks, and 7 people answered, I saw 7 flocks. That was their answers on day 1. All right, day 2, they had different answers. And so what the question wants us to figure out is use the mean value of each data set to make an inference about the number of flocks observed each day. So if you'll remember the other day when we were talking last week, we talked about the difference between the mean, the median, and the mode. And so the mean, remember, is the average. Whenever you say like the average, you're referring to the mean. So the average is almost like the middle between all of the numbers. And so what you do mathematically, I'll kind of go through this quickly because we talked about this already, but what you do mathematically to figure out what the mean is you add all of the data together and then you divide by the total number of data points. So in this instance, we have, well, what's our data? We've got 4 plus 4 plus 4 plus 4 plus, okay, 5 plus, so see how I'm getting this? This is 4 plus 4 plus 4 plus 4 plus 5 plus 5 plus 5, all the way up. For all that data, we would do that. And you could write this all the way out. If you do the plus sign, it will give you the right answer. But remember what addition is. Addition is like a shorthand way of writing exactly that. So instead of writing 4 plus 4 plus 4 plus 4, what we could write instead is 4 times 4, where this 4 is the number of times the number appears. So see that we've got 4 instances of the number 4. And then this number is how many, like what number are we counting, right? So what we can write here is for day 1, the mean is 4 times 4, so that is 4 instances of the number 4, plus we will add how many times was the number 5 there. Well, we saw the number 5 7 times. So we'll write 7 times 5 for that. So again, there were 7 times where the number 5 was listed. And we'll do that again for plus the number of times 6 was listed. Again, there were 7 times 6. Or 7 times the number 6 was mentioned. And then we will add, here, I'll get rid of this for a second so that we don't get distracted by it. So plus, after this, how many times is the number 7 listed? Again, there were 7 times the number 7 was listed. So all we've done here is we've said 4 plus 4 plus 4 plus 4 plus 4 plus 5 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 plus 6 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 plus, and you get it now, 7 plus 7 plus 7 plus 7 plus 7 plus 7 plus 7. So we've written that as short as we can by writing it this way. If you don't remember how to do the multiplication, again, you can just add all that up. You can just type them in, plus, 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 plus. Divided by 25. That's how many answers there are total. So if you count how many dots there are here, there's 25. It tells you there's 25 participants. You could add up that 4 plus 7 plus 7 plus 7. That gives you 25 as well. And so when we do that, what we get is, calculator, 4 times 4 is 16 plus 7. Oh, sorry, I don't know how to type this as easily here. So we can do 4 times, oh my gosh, my calculator skills. 4 times 4 is 16. So we could write, simplified, we'll write 16 plus 7 times 5 is 35. Plus 7 times 6 is 42. Plus 7 times 7 is 49. And all that is still going to be over 25. So if we take 16 plus 35 plus 42 plus 49, we get 142 divided by 25. And I'll prove to you that this is the same thing. So if we did this instead, where we did 4 plus 4 plus 4 plus 4 plus 5 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 plus 6 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 plus 7 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 is 142. All right, so 142, and then that is all divided by 25. 5.68 is our number. So I'll get rid of some of this work here just for space purposes. All right, this right here, 5.68. So that's the mean for day 1. Day 2, the process is exactly the same. So I won't write this out physically with the mouse, but I'll show you. We would add up all these points. I'll even do it the slow way here. We'll do, how many times do we have the number 2? We got it 8 times. So this is 1, 2, 3, 4, 5, 6, 7, 8 times, 16. Plus, how many times do we have 3? We've got 3 7 times. So we'll add another, we'll add 3, 1, 2, 3, 4, 5, 6, 7 times. Plus, we will add the number 4 6 times. 1, 2, 3, 4, 5, 6. And then the number 5 appears 4 times. 1, 2, 3, 4. So in total, if you add up all of the observations of the hikers on day 2, they only got 81 times. And it kind of looks like that, right? Like, look, these guys are answering 2, 3, 4, 5. This group is answering 4, 5, 6, 7. So it makes sense that we're at 81 here. So we'll take 81 and we'll divide that by the total number of answers is still 25. And we get 3.24. 3.24. I will check my answer by doing the multiplication. So we should have had 8 times 2 is 16. Plus we're going to have this 3 times 7. 3 times 7 is 21, so we'll add 21 to that. 4 times 6 is 24, so we'll add 24 to that. And 5 times 4 is 20. So that's 81 divided by 25, 3.24. So these are our two means. We've got 5.68 and 3.24. And so now what we're trying to do is use the mean value of each data set to make an inference about the number of flocks observed each day. So what can we observe? That there were more flocks of geese seen on day 1 than day 2. See how the average number of flocks of geese that any given hiker saw, the average number was 5.68 flocks of geese. And then the average number of flocks of geese that was seen on day 2 was only 3.24. So on average, people saw less geese on this day. So even if you picked like one individual person, maybe this data point and this data point were the same person. So the first day, person number 1 saw 4 flocks of geese. and person number 1 on day 2 saw 5 flocks of geese, they saw more flocks of geese, but the average of the whole group has gone down from day 1 to day 2. So that's your inference right there. All right. I hope that made sense. I'm sorry I can't go back and forth and ask you if that made sense to you, but tried to explain that. So anyway, we'll go on to the next one. So question number 6 is the drama teacher wants to determine where the drama club should go to celebrate their final performance. Which of the following is not a representative sample? Select all that apply. So if we're trying to figure out what is a representative sample, we need to ask ourselves, does this smaller subgroup that we've selected, does this subgroup accurately reflect the characteristics of the larger population from which it's drawn? Basically saying, if we've got a whole bunch of people, say each of these are people, and we say, hey, let's just take a look at these people right here, we're asking ourselves, do these people represent everyone? Yes or no? So that's what we have to consider on this. So let's go through each of these. Students who do not act. Do you think that students who do not act are representative of the drama club? I would go out on a limb and say that the answer is no. Students who don't act, and there are people that are a part of the drama club, but that's one smaller group. If you're only asking the people who do the lights and the sound, that's not really getting an accurate reflection of what the whole group would want. So I would say that students who do not act is one of the samples that is not representative. So this is one of the answers that I would check. I would shade this box or whatever, because it's asking you what's not representative. What if they did every 4th student selected from an alphabetical roster of the club? So now what you've got is this whole list of students, and in no particular order, or rather in order that is not determined by anything other than their name. Their name is more or less random, right? You can think about it as in well, if you're reading down the list, you'll get okay, here's an actor in scene 1, and then here's the lead role, and then here's a supporting role, and then here's a person who's doing the lights, and now here's one of the teachers, and now here's this. You're in no particular order. It's pretty random, basically. If you're picking just every 4th person, that would be really random. Now, what you wouldn't be able to do is say anyway, so picking every 4th student selected from an alphabetical roster in the club, that is truly random. So that's one of our criteria, right? And it is representative of everyone, because you're going to get some people who are doing the sound, some people who are doing the lights, some people who are acting, some people who are supporting, right? You're going to get a bunch of different groups of people. The subgroups are going to be picked in that. Plus, if you're picking every 4th student, you're asking a quarter of the students. So if it was just ask one student what they want, well, that's not really representative, because there's not enough. And for a lot of other reasons. So every 4th student, that's pretty representative. So I would say that this is a good one. And for that reason, you would not shade it in. Now, as a side note, the reason you can't just pick the first quarter, say you've got, I think I drew 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Say each of these lines represents a name, and say, well, I want to pick the first quarter of students. Let's just go with these students. That should be representative, right? Because, well, it's randomly selected. But you may be able to argue well, these students, if they're all alphabetical, they all sit next to each other in classes probably, so they may be friends with each other, and so maybe they're more likely to pick something that's not representative of the group. A little bit of this is trying to just use your own noggin, right? Just ask yourself, would this be fair? If your teacher asked a small group of close friends what they want, and it's not, and those people are nothing like you, they'd be hey, that's not representative. So part of it is just asking, is there a reason to think that they may not be representative of the sample? So a good example of that is students who appear in the first act. So I could see this going either way. Students who appear in the first act, I guess technically are still the actors, right? And so you're not representing the people who are on the sound crew and the people who are doing all of that, the lights and stuff. And so already you're kind of picking a subgroup that has different interests than some of those other groups. So I would say that this one doesn't count. If you were looking at just the actors, it's like maybe that counts because you've got the lead probably, you've got some supporting roles. Like there's a pretty good chance that that's maybe a little bit more fair. But still, it's like, well, who's going to appear in the first act? It's like the lead is going to appear in the first act, so that's not very fair to everyone else. Like, if you really want a representative sample, you need to choose people at random. So I would say you shade that one in as well. We've got students with supporting roles. This is kind of similar to what I just said about, like, hey, we've got a lot of other groups. Like, there's people who are the lead, there's people who are the sound crew, there's people who do, like, makeup, like, there's all those different groups, and they all have different skills, they all have different talents and personalities, and, like, they're not being represented at all. And so I would say that this is also not a representative way to pick people. And then finally, we've got students whose names are randomly selected from a hat. Well, now that's perfect, right? Because we've got students that are from all those different subgroups. We've got an equal chance of any one student being chosen. As long as we pick enough students, then this is a good one. And so you would not shade that. So that's my answer for that. Again, always just asking yourself, does this subgroup that I picked, do they accurately reflect the larger group? And if the answer is yes, then they're representative. And if the answer is no, then they're not. So hopefully that makes sense for you. Okay, let's move on to 7. Let's take a look at which of the following measures of center can be used to compare two data sets. So I think that this was a little bit misleading with the wording as well. I actually took a screenshot of this and put it in an AI math bot to give me the answer because I wanted to make sure that I was answering it the way that your teacher wanted you to. The way that this is worded, you could read this as like, which of these ways of measuring data could you use to compare two data sets? But I think the question is trying to ask, like, which of these are measures of center specifically? Like, they measure the center of the data and then can be used to compare two data sets. So that's what we're going to be looking at. So we already looked at mean when we did question 5. Remember that the mean takes a bunch of different data points. Let's say we've got this number line and we've got some data points that fall like on the lower side, maybe some in the middle a little bit, and maybe like that. So if each one of these dots, like this side represents low numbers, this side represents high numbers, and each of these dots represents an answer, like we would say, okay, well, the average is probably right around here, right? Because we've got, if we added this up, say that this number is 1 and this is 10, we've got like 1, 1.5, 2, 2.5. We got like a 9 and a 10. Say we found the middle to be right there. Like that would be something that is a measure of center because the mean is literally telling us what is the mathematical center of all of our data points. And for that reason, I think that the mean would count as one of the measures of center. Now we'll look at the interquartile range. And so again, we were talking about this when we did the box and whisker plots. But when you get the plot that looks like this, and then you've got, it's a little hard to see the black on black, but you know what this looks like. So when we look at the interquartile range, that is specifically referring to this area. And the reason it's called the interquartile range is, well, listen to the word quarter, right? Quarter, you know that as from money. That's a quarter is 1/4 of the data. So if we're looking at the inner quarters, remember the box and whisker plot divides our data up into 4 sections. We're basically saying 25% of the data falls here, another 25% of the data falls here, another 25% of the data falls here, and the rest of the 25% of the data falls there. And so we're looking at the inner quarters, the inner 25%, the inner quartile range, as in from lowest to highest. And so any of the values that fall within the middle 50% of a data set is the interquartile range. That's what that's measuring. And so while that is useful for comparing two data sets, it is not specifically a measure of center, because it's not measuring the center. It's not measuring the dead center. It's measuring all of the values that are even kind of close to the center. And so interquartile range is not an answer for this. We've got median. Remember we talked about the median was when we had a list of numbers. Like, here I'll type. If we have like 1, 2, 2, 3, 4, 6, 8, 8, 10. So if we had this data set, the median is specifically referring to which of our data points is in the dead center. So not mathematically what is the number that's in the dead center. Remember when we were over here on number 5 and we got an answer of the average on day 1 was 5.68? Well, no one saw 0.68 flocks of geese on a given day. You can't see 0.68. That's like if you were like, hey, what's, how many was the average number of people that attended a concert at Hershey Park Stadium on a, during the summer? And it's like, well, we got that, there were 31,568.2 people on average attended a concert. Well, you can't have zero point 0.2 of a person, right? And so this is basically saying the median is like which actual data point was the one in the dead center. And so to find that, all we do is we take a look at which number, we just cross them off one at a time. So let's take the lowest number and the highest number, and we'll get rid of both of those. Now we'll take the second lowest number and the second highest number, get rid of those, and we'll keep doing that until we reach the individual data point that is in the dead center. And that number right there is the median. That is a measure of center in a sense. That is measuring like a number that is in the dead center of the data. And remember, the point of the median specifically was if you've got a number, like say this last number was 1,000, then your mean is going to be a number that is higher than almost all of the data set. Like your mean here, let me think real quick, is going to be close to over 100. It's going to be over 100. And so if you say, hey, the mean is 100, that's not actually representative of like what most of the data is. So the median kind of helps prevent outliers while still measuring the center. We've got the mean absolute deviation. And so that number is basically a measure of how spread out is the data. Let me figure out how mathematically how you find that. Mean absolute deviation. You take the sum of the data and you subtract let me find real quick, how do I find the number mathematically? .4 minus 3. Sorry, I'm just trying to figure out how I actually mathematically find this. This is what I'm looking at over here. I'm looking at the formula. So you take the sum of the numbers and subtract data values in the set. Is that just the number of data value? No, this is the number of data values. Average value. So this is the average. I'm trying to figure out what data values in the set means. Take the data values in the set. Oh, interesting. Okay. So I guess to find the absolute deviation, you take how many answers there are. So in this case, like, Jennifer had 4 apples. Oh. Okay, I see. All right, sorry, I haven't done this for a while. This is basically saying, like, how far away from the average is any given data point. So what you do is, that's like what each of these numbers are. So see how if we went through, we found there's 4, 3, 3, 2, 5. So in order to find the mean, what we do is we take 4 plus 3 plus 3 plus 2 plus 5. So we've got our mean and then divide it by how many answers there were total. So Jennifer had 4 apples, Amelia had 3, Noah had 3, Daniel had 2, James had 5. On average, everybody had 3.4 apples. That was like the average number of apples that any given person had was 3.4. What you do is you take that average number and you subtract the individual answer. And look what that gives us. That basically gives us how far away from the mean is that number. So we'll take 3.4 for in this example. The mean is 3.4, and we subtract. Jennifer had 4, and that gives us negative 0.6. These little bars mean we take the absolute value, aka if there's a negative, ignore it, and we find that Jennifer was 0.6 away from the average. Right? You can see that how the average is 3.4. She had 4, so she's 0.6 away. Amelia was a little closer to the average. She was only 0.4 away. Noah was 0.4 away. Daniel was 1.4 away. James was 1.6 away. And then this is like the deviation for any given point, as in how far it has deviated away from the mean. And to find the average of these numbers, we do the exact same thing as when we took the mean. We take them all and add them up and divide it by the number of answers there are. And now that tells us how far away, on average, it are the data points from the mean. So you'll notice what happens is, if you've got a data set that's really spread out, you'll find that the absolute deviation is very large because the data set is spread out over such a wide range. Whereas if it's very, very tight, then the average will be smaller. So I'll show that to you graphically. Say we've got 2 sets of data, one like that, one like that. And say we've got the first set is like this, and the second set is like this. Well, look, the mean of this data set is going to be right in the middle, but the mean of this data set, we got a bunch that are really low, a bunch that are really high. The average is like still right here in the middle. So the mean absolute deviation describes like how far apart are the data points from the middle. So you can see in the first example, the data points are spread out not very far, whereas the bottom one, they are spread out really far. And so mathematically what you would find is, say like the average here is like 5, and all these values are like 4 at the lowest or 6 at the highest. You'll get a mean absolute deviation of like 0.1 or 0.2, somewhere like that, right? Whereas down here, because if the average is 5, but this is like the answer is 0, and up here these numbers are in like the range of 10, you'll find that the mean average deviation is like 5. Like it's very far away. And so all that to say, the mean absolute deviation, that measures how spread out your data points are, but it does not measure the center. And so this is not an answer. And now finally, this is the easiest one. This is the range. So the range is literally just what is the lowest number and what is the highest number. So if we've got a data set and it goes all the way, say that this number is 0 and this number is 10, and I won't draw all the numbers, but you know, we've got numbers that go all across. Well, this number right here, let's say that specific data point is 10 and this specific one is 1, then what's the range? Well, we just take 10 minus 1, and that gives us a range of 9. And so that just tells us that our data at the most is 9 units away from each other. Again, not a measure of the middle of the data set. So for this one, the only 2 answers are the mean and the median, because they are the only ones that measure the center. All of them can be used to compare 2 data sets, but mean and median are the only ones that are the measure of center. All right, we're doing good. Last one. Andy is comparing how long 2 tablets can be used after being fully charged. And so we've got tablet A has a mean usage of 540 minutes, which is about 9 hours. Tablet B has a mean average usage of 593 minutes, which is about 10 hours. The median for tablet A is 560, and so it seems like, why would the mean be lower than the median? Well, there were probably a couple of instances where the tablet died really quickly. Like if you've ever used GPS, or maybe you're watching like YouTube drains your battery faster, like there were a couple of instances where the phone died really fast, but then most of the time it was still a little higher. So maybe that's why the mean's a little higher than the median. Or sorry, the median's a little higher than the mean. Tablet 2 had a median very similar to its mean of 589. The interquartile range of this is 21. Tablet B is 13. And the mean absolute deviation of tablet A is 6, and tablet B is 2. And so what does that tell us? That tells us a couple of things. So what they want us to figure out is to use the measures of center to make an inference about the data. So what are our measures of center? It's just the mean and the median. Those are the only two that are looking at specifically the center of the data. So what do you notice? Like, does tablet A or tablet B have better performance? Well, we see that tablet A on average only lasts 540 minutes, where tablet B lasts 593 minutes. So it's almost an extra hour longer. So in the mean department, tablet B wins. And the median even, look, the median is even larger for B as well. So there's really no argument to be made for tablet A. Tablet B is the better tablet in terms of the measures of center. Now we'll look on part B. Part B is based on the data which tablet performs most consistently. So if you're looking for a tablet that's consistent, you wouldn't want a tablet that sometimes lasts 20 hours and sometimes lasts 10 minutes. And so we want our data to be really close together. And so if we look at an interquartile range, remember that's the data point, or this is measuring the data of the middle 50%. So we're looking at these values. I'll get the red out again. We're looking at this value. This is the interquartile range. Specifically, what is the highest number and the lowest number within that interquartile range? So have you ever heard the term percentile? Basically means like what percentage of people are you better than at something. So if you're in like the 99th percentile for baseball, that means you're a better baseball player than 99% of people. And so in the data point here, you would be like right there. You're better than all of these people, right? So we're looking at this data point, which is the 75th percentile, aka this data point is greater than 75% of the data. It's greater than all of that. So that's one of the points we're looking at. And we're looking at this point, which is the 25th percentile. So this data point is greater than all of these data points. And we're trying to figure out between the 75th percentile and the 25th percentile, what is that range? So let's say this data point right here is like, say it's a 40-yard dash time is what we're measuring. And a person who is better than 3/4 of all the people, say they run a, or maybe here, that's a bad example because it'll be a little confusing because a lower time is better. So let's say like a basketball player, how many, or like let's do like RBI or batting average rather. Let's do batting average. So let's say like a player who has a better batting average than 75% of the players. Let's say they've got like a .305, and then a person who's only better than 25% of the players, let's say they've got a batting average of like .180. So what is the interquartile range in this case? Well, you take the largest, you take the 75th minus the 25th. So we take .305 and we subtract .18. This is the interquartile range. This is basically saying like how spread out is this data? Because the bigger this number is, that means the more spread out this data point and this data point are. And so this number is kind of telling us like, well, they're only .125 away from each other. We're not looking at how much better is the absolute best person than the absolute worst, because maybe you've got some real stinkers, or maybe you've got some real like prodigies. We want to look at someone who's like good, like well above average, but not like a freak of nature. And we want to look at someone who's like bad maybe, but also not like a trash can. And so that's what this is giving us. How much better is like a person who's pretty good versus a person who's pretty bad. And so in this case, we've got the tablet, right? This is in minutes. The 75th percentile of tablet A died 21 minutes slower, or it lasted 21 minutes longer than the 25th percentile. So this tablet A, if you measured all of the different times that you were using the tablet, the time that it performed better than average would be like 21 minutes faster than the time it performed a little bit worse than average. Whereas tablet B, that was only 13 minutes, aka the difference between a good performance and a bad performance for tablet B was not as much as for tablet A. And so this tablet B is looking to be more consistent so far. And then if we look at the mean absolute deviation, that is a similar measure. Remember that this is talking about, on average, how far away is any given data point from the center. And so what we're looking at is tablet A on average is 6 minutes away from the center, whereas tablet B is only 2 minutes away from the center on average. AKA, on average, tablet A's data points are farther away from the center than tablet B's are. And so, again, I think you can conclude, I forgot to write B here, but this is tablet B. I think, again, you can conclude that tablet B is more consistent. And so I know I gave a really long-winded explanation. So if you were just writing this down, you would write tablet B is better because it lasts longer. Or you would even write like tablet B is better because the mean and median prove that tablet B lasts longer on average. And then part B, tablet B is more consistent because the interquartile range and the mean absolute deviation show that the data points for tablet B are closer together than for tablet A. So I know I gave like a long explanation for some of that stuff. I hope it made sense to you. Again, your teacher just wants to see that you understand some of this stuff. And so if just remember, anytime you're making inferences, like make sure you show not just that you know what the right answer is, but why you know what the right answer is. So there's an overall look at the whole thing again. And I hope this is helpful. So appreciate it, man. And just as a reminder, I will not be around next week on the 28th. So our next time together will be here on June 4th. But look forward to seeing you then, man. Good luck on your... oh, sorry, not June 4th, June 5th. I won't be here on the 29th. I'll be here on the 5th. June 5th will be our next time. So have fun on... or good luck on your test, man. Appreciate it. And looking forward to seeing you.